that was the housekeeping. So let's get started with today's content. My name is Michel van der Sloot. I will be doing the presentation today. I have a long history with PLAXIS. I started with PLAXIS in 2004. Part of the presentation will be done by Chris Callan, especially the demonstration part that we pre-recorded here today. So that the demonstration from Geostudio side, how we can combine PLAXIS and Geostudio, will be done by Chris Callan, who is the director of geotechnical analysis for Geostudio within Sequent. And so that will be today's content. Before we get started, I would like to have some input from you, just for my reference, and it's also good to understand how people are using software to run their slope stability analysis. So if you can answer this question, that would be great. Are you using PLAXIS 2D, using finite elements? Maybe you're using a limit equilibrium method, or the method of slices, or method of columns, depending on how that's formulated. Could also that you're already using both finite elements and limit equilibrium method to calculate the factor of safety for slopes. Maybe you're predominantly using analytical solutions. Think about tailored charts or other kinds of analytical solutions. Or you have an in-house spreadsheet that you actually use to compute the factor of safety for different types of slopes. If you have maybe another method, please let me know in the Q&A box, so we can also figure that one out to make sure that I understand where people are coming from, to help me maybe to add some additional pointers during the presentation. So pick one of these, then I will move over to the next slide. So either using PLAXIS 2D and finite elements, using limit equilibrium, maybe already combining finite element method and limit equilibrium method, or using analytical solutions, or predominantly using a spreadsheet. It could also be that you're using something else. Please let me know. Then I will move over to the next slide. So today's content, let's first talk about what we mean with slope stability, why we do it. That's, I think, very important to get started here, of course. Then how do we determine this factor of safety for the slope stability using limit equilibrium, LEM, or how to use it with finite elements, so FEM. Since we talk here from a PLAXIS point of view, coming from a finite element solution, the question is, why should I add limit equilibrium to my analysis? PLAXIS already can give me a factor of safety, right? So why should I add that one? Then we talk about how we can have interoperability between PLAXIS and Geostudio, and we're going to demonstrate this in a case with the hillside stability. So to show you how you can actually benefit from using finite elements and limit equilibrium together. And finally, we have conclusions and summary. I see somebody's not seeing the slides. If you don't see anything moving forward, make sure that you refresh the browser. That's usually the best approach to make sure that you let also. Okay. I see I have here the wrong poll. My bad. I see I made a mistake. Poll question. Okay, so here we have the results. I see here that the results from the poll, we're having about 15% already using PLAXIS predominantly. 35% are using the limit equilibrium method, and already a great portion of the people presenting here today, it's 45% are already combining both. So that's great. And still, a lot of people are also, about 5% of the people attending here today, they use slope stability from spreadsheets. Okay, great. So if we talk about slope stability, we usually have to deal, of course, with a slope in our geometry. That could be an earth fill, or the dam, embankment, levees, natural slopes. And once we analyze these are, especially when we design these slopes, they we require them to meet a certain design factor of safety. Um, so it has to be according to the standards. Usually there's a local building code, or maybe you're using Eurocode, and you have to prove that you have a safe solution here. Now we can assess this by numerical models. We already discussed this already a little bit in the poll. Um, and the goal of these numerical models is to prove that actually um, the goal of these numerical models is to prove that the situation that we have, it it exceeds a required minimum factor of safety. Of course, for the ideal situation, especially if you have to design something, you want to sort of be really close to your factor of safety, but at least the design should have a minimum factor of safety to make sure that it is a safe design, and that will be approved by local authorities to actually be a safe design. And the question, of course, is what is a factor of safety? I think it's always good to realize that how do you define your factor of safety? What is required? There can have many possibilities. If we take, for instance, this example here where we have our load on top of soil. Question is, okay, so we have this load Q on top of the soil, which is controlled by the weight of the material, the cohesion, and friction angle to determine the shear strength. We can define a factor of safety for the strength based on the available soil strength divided by the mobilized soil strength. So that would be one definition. Another definition would be the factor of safety for the load, where we actually have the working load condition. So in this case, the load Q. We might increase that load until the model fails to converge to a solution. And then we have the failure load over the working load. We can also define it as the factor of safety. Now, we have to realize that the factor of safety for the strength is almost always not the same as the factor of safety for the load. There's just a different definition of the availability of the available space for the safety. Now, if we look at PLAXIS, if we look at limit equilibrium methods, the factor of safety that we consider in the standard safety analysis will be the factor of safety for the soil strength. How PLAXIS deals with this is that we have a factor of safety in the finite elements, also known as the phi-c reduction, and it's based on the reduction of shear strength. And we do this with a gradual reduction of the strength. So if we start with the original Moore column failure envelope, for instance, for the Moore column model, the hardening soil model, soft soil model, we start with this red line as the Moore column failure criterion, and then with the gradual reduction of strength. So we apply we increase a total multiplier called the sum MSF, and with that we actually lower the strength of the soil. So we reduce the tangent phi, we reduce the cohesion, and with this factor, so it's a linear reduction of this, and it's a global factor. And then we're going to reduce it until we get to the green line, and so we gradually try to reduce it, and then PLAXIS still tries to find equilibrium. Now we continue this process until we cannot further reduce this factor anymore. And this, of course, means that we have to do a check on the converged solution. We usually do this by picking a relevant point in the failure zone, and then we follow those deformations. And once we have ongoing deformations without a change of the factor of safety, or the sum MSF factor, then we can assume that this is the factor of safety for the soil strength. Note that we have a global reduction via one reduction factor. So a typical graph would look like what we see here on screen with the blue line, is that we try to reduce this sum MSF, which is on the vertical axis. So we increase the sum MSF, which reduces the soil strength, and the soil strength is for all the soil models in the model. And then we try to reduce it, and we have to sort of make sure that we reach a certain plateau. We might have a sort of local peak before we actually reach this plateau, so it's good to check the relevant control point. And in this case, we look at the incremental displacements in the PLAXIS output results. To get more information, we have a link in the resources that points to a previous cover corner we did on the factors of safety. And if you want to have more details on the scientific background, there's also a link to the articles from Brinkleven and Bakker on nonlinear finite element analysis of safety factors. So that's where this approach was first proposed. Now, if we look at limit equilibrium analysis, that method is a bit different. Of course, it's not the finite element method, but it's a limit equilibrium method. So how this works is that we try to find the factor of safety that brings the system into a state of limiting equilibrium. So that means that we sort of also will reduce the strength of the soil until we just have equilibrium. It always starts with a prescribed slip surface. So you have to specify in the limit equilibrium method, it will start with a predefined slip surface, and it then tries to find on this slip surface the minimum required equilibrium by reducing the strength. And then the limit equilibrium method will use many of these trial slip surfaces to find the one which has the lowest factor of safety, and that's what we call the critical factor of safety. To run the calculation, the sliding mass, and so it's recognized here with this circle, it will be divided into several columns, and each column will represent a portion of the soil. So it's the vertical column, and with that we can take into account the variation in, for instance, soil layers, water pressures, loads on top of any of these columns. So we can then take that into account in each column, and each column we will look at what we call the free body diagram, where we can have of course the self weight of the soil of that column, maybe a load on top, and then on the base we have a normal force and a shear force acting on the base. And on the lateral side we have what we call inter-column forces, so that's a shear force, and a normal force acting on these lateral sides. That will form the free body diagram, and of course that needs to be in equilibrium, and we have to make sure that we calculate this to be in equilibrium, not only of course for the individual columns, but also the global equilibrium should be satisfied both for the forces but also for the moments, depending on the type of limit equilibrium method you choose. Think about Bishop or Spencer or Morrison Price. These will take not always all the equilibriums into account. So if you go with Morrison Price, for instance, then both the equilibrium for forces and the equilibrium for moments will be taken into account, and we also will take the interslice forces into account. To calculate the normal force here, so that will be the normal force acting on the base, we have to make sure that we and this is then used to make sure that we actually can calculate the vertical forces equal to 0. we have to take into account the self-weight of the material, so that's shown by the W. Then we have delta X, which is the difference between the intercolumn shear forces on the left and right. And D might be a point load that we put on top of this column I. And then, of course, we have the cohesion and the friction angle for the material that we are looking at the base of the column, to make sure that we actually can calculate the shear strength of that part. What's good to note about that is that we also take the factor of safety F into account in this equation to have a state of limiting equilibrium. And this F, we can calculate it based on the available shear strength over the mobilized shear strength. And then we can, of course, rearrange it such that we can use the mobilized shear strength, Sm, to divide it by the shear strength over the factor of safety. And with that, we can easily calculate this limit equilibrium. And with this method, we also find the factor by which the strength should be reduced, so that we just have a state of equilibrium. That's the core of the limit equilibrium method here. So, in order to have to satisfy static mechanics, we have to make sure that we have a system which is in equilibrium, both in force and moment. And so we have two factor of safety equations. One will be the factor of safety for the force, and one will be about the moment. And we also have to realize that the intercolumn shear forces that we have, so the forces that we have on the lateral sides, they are also a function of the factor of safety. So that requires that we will have a set of nonlinear equations, which will require us to calculate these in an iterative solution. We're actually going to make sure that we determine the intercolumn shear and normal, base normal, with this factor of safety for the moment, Fm, and the factor of safety for the force, Ff. So we can calculate those based on that. And then we use a scaling factor lambda to make sure that the factor of safety for the moment and the factor of safety of the force are equal. Because then, of course, it makes sense that we have a proper situation where we actually have the same reduction of strength to satisfy both the equilibrium for force and the equilibrium for the bending for the moment. Now, and that's also why it's important to see the convergence of the moment and force diagrams in terms of the lambda, to make sure that we actually see both of these lines. So the pink line is the equilibrium of force scale with this lambda factor, and on the blue line we actually see that we see the development of the moment for the factor of safety. And then we see at the cross point, we actually have both the same factor of safety for an state which is just in equilibrium for the force, and one which is just in equilibrium for the moment. So with that, we can satisfy both conditions using the same factor of safety. So both are just in a state of equilibrium. And of course, if it would be lower, then probably either the factor of safety for the moment might not be satisfied, while this for the force, or the other way around, of course, depending on the model. That's why it's important that we have this this point where we actually match the factor of safety for both the force and the bending moment. So If we look from PLAXIS, which is to the finite element application, we also realize that the safety analysis using the phi reduction is a very powerful tool. You don't have to specify anything up front. The most critical slip surface, or the slip surface with the lowest factor of safety, might not be critical for a project, but if you just look at the most critical slip surface in terms of the factor of safety, that slip surface is an outcome of the analysis. So the finite element will automatically find that for you. And because of this, the shape can be any. It can be circular, can be non-circular. We can have convex or convex shapes. It really determines on how the strength reduction is applied based on the starting stress state that you have. But not in all cases that's what we need in our analysis. Sometimes we need more. We do not only need maybe the slip surface with the lowest factor of safety. We might also want to have more info in the rest of the model. What would be the factor of safety for other parts of the model? We will look at maybe we want to check local and global stability. Sometimes PLAXIS will give you a very local instability, while actually you're more interested in a more global mechanism, or maybe a different part of the model. Maybe also want to know a bit more variation in the factor of safety for different slip surfaces. So for instance, maybe there are different parts of the model where actually the factor of safety might be 1.6 for one part, but for other parts, yeah, it might be 1.6 or 1.7 or 1.8. That's something you don't know from the finite element analysis. And maybe also a very important requirement is that if you have a design or analysis done, is that local design practice dictates that you also need to have a limit equilibrium analysis. So you also want to then, of course, not only rely on your PLAXIS analysis, but you actually have to run a limit equilibrium analysis also to prove that your design is safe. So how does that look like? So for instance, we take this dam example. It's taken from our tutorial manual, and we see here we have a dam with or an embankment with a left and right hand slope, both with a different angle using the same material. If we run the finite element analysis, this is what we see in terms of slip surface, which of course makes sense. The steepest one gets the most critical slip surface. But what if our real situation is that so this gives a factor of safety of about 1.8. But what if we have only nature on one side, and on the other side we have industry, buildings, residents? Do we still need to have the same factor of safety, or the same criteria for both sides? So, in this case, since there are a lot of economic activities on the right-hand side, you also want to know what will be the factor of safety for that side. So what will be the factor of safety for this side? Finite elements will not give you this number, but we might also use other methods. Now, another example would be this dam. It looks a bit more complex than the one that we had in the previous case, and you can recognize we have different parts, different thicknesses of the brownish red layer. Do we have an upstream side? So the question would be, okay, PLAXIS, you run the PLAXIS safety analysis, and it will give you this result with this slip surface. But the question would be, what would be the factor of safety for the upper slope? Maybe you want to also check the global stability. And maybe you also want to know what would be the factor of safety for and my stability from the upstream side. That's something that finite elements cannot give you. With limit equilibrium, we can really specify where we start, where we have an entry point and an exit point of the slip surface, where you can quickly run the analysis. So next to finite elements, we might also need limit equilibrium. And that's clear from the two examples that we saw in the previous slide, that we also would need to have additional tools to enhance your finite element analysis to also get limit equilibrium results there. Of course, we can do this manually. We can create the model in PLAXIS, and maybe we can also run and create the model in Geostudio Slope W. But of course, it's very tedious work. Takes some time. You don't always have this time in your project. Also, it's not the most fun thing to recreate the geometry in the other application. So we have developed a Python script where we'll be able to quickly move from one application from PLAXIS to Geostudio. And this tool is now available on our Bentley communities. You can find the link in the resources, which includes a description of features, limitations, and the page will also be a place for any future updates. So this is an additional tool. This is not automatically installed with the software, but you have to get it from the Bentley communities webpage. So this is how the tool looks like, and the workflow would be that we have to start from PLAXIS to the Connect Edition version 22, update 1 or later. Update 1 is the current latest version, but we'll make sure that it also works for the next update. Of course, we also need to have a limit equilibrium software installed. In this case here, we're going to talk about Geostudio Slope W version 2021 or 2022. It will also support PLAXIS to the LE Connect Edition version 21. Yeah. And of course, we have to make sure that we have downloaded the tool and that we have put the tool in the desired location. We just then select a face in the PLAXIS 2D model, and then using the tool to convert the PLAXIS 2D face configuration to a limit equilibrium model. So that's the current conversion that we have. You select a face in PLAXIS. That specific face will be converted to a limit equilibrium model. You can then automatically open the limit equilibrium software from this tool by just a click of a button. And then we just have to complete the setup. Most of the materials we can actually move over in terms of the strength criteria from PLAXIS to limit equilibrium. In some cases, of course, the strength method determination is not the same from PLAXIS as in Slope W. So in this case, you have to make sure that you adjust your model in Slope W. And limit equilibrium, of course, has certain requirements to set up your slip surface definition. So that's something you also have to do when starting the limit equilibrium analysis. Maybe it's good that we actually show this in an example, how this works and what can be done. So I'm going to start here showing the example from the road along a hillside. The idea would be that of this case is that we have a natural slope based on siltstone with private land, which you see a bit on the left-hand side of the image. And there we need to construct a new road. So the road, which is indicated, the original slope is indicated with the dashed line. And then we have to construct a new road. So we have to do some kind of soil removal and a fill, creation of a fill to put the road on top. And in an analysis, of course, we're going to determine the factor of safety from the original hillside. And then the new road construction, we have to look at the summer conditions, which are shown here. But if you also, in winter conditions, the water table will be raised due to heavy rainfall. So that means that our pore pressure distribution changes. So we have to make sure that we also check the stability in those cases. And they have proposed here, in order to meet the desired factor of safety, to install soil nails, which are indicated here with these magenta lines. It's good to note that we have a critical factor of safety for this approach to compose of two parts. One is that we do not want to lose the road. If we lose the road, the road is completely lost. That's a huge economic cost. Of course, we have to replace it, and of course, the road is also out of service for a very long time. For that case, the factor of safety that's required would be 1.8. Now, if we look at the loss of service, which means if the top slope actually fails on top of the road, so if this slope actually fails and goes onto the road, of course that's also not good, but the road will just be we just have the rock fall on top of the road, which we can easily remove, and so then that economic impact is much less. For that case, the authority have said that the factor of safety should be at least 1.6. So with that in mind, let's start showing how the PLAXIS model looks like, and then after that we're going to look at the limit equilibrium solution. Start the screen. So here we see the PLAXIS model loaded, and we recognize here that the siltstone is divided in two parts. We have the top weathered siltstone, and then below is the intact siltstone. And if we look at the properties, the weathered siltstone, that's the green layer here. It's defined here with the unit weight, stiffness properties, strength properties. And in this case we use the more column model because we're mostly interested in the stability, the factor of safety. And if we look at the intact siltstone, it also has these properties, and the strength properties are a bit higher. Another difference between the two layers is that since in these winter conditions there is a high rainfall, that means that the water table, if I look at the winter conditions here, water table will be different due to the high rainfall, so you can see it represented here. So also the hydraulic conductivity is set up for the two different layers. So after we start the initial phase, we're going to do the construction. Let's hide the line loads here to make it easy for us to see. So here at first the top of the embankment is excavated, and actually in the next phase we're going to construct the fill, and on top of this fill we're going to construct the road. The road is shown here. The loads are inactive until we add the traffic load in this phase. And after that we're going to determine the factor of safety in summer conditions, and for that we will start the output program. I already run the calculation, so we do not have to wait here for the calculation to finish. So here we see the results of the safety analysis, and for that I'll have to look, of course, to our incremental displacement, so we can see the shape of the slip surface in the summer conditions. So that's still with a low water table. And also I can look at the incremental deviatoric strain to recognize the shear bend, and you can see we have a nicely formed slip surface which is just going over the, if we go to the conductivity plot, you can see over the interface between the intact siltstone, the blue layer, and the green layer with the weathered siltstone. Now if we then go have a look at the factor of safety development, we see here the development of the selected node in the failure zone, and we see that we here reach a factor of safety about 1.32, which is not a very high value, especially if we want to make sure that our factor of safety for loss of the road is a factor of safety of 1.8 or higher. Now if we're going to look at the winter conditions, first the water table will be increased. We'll run a groundwater flow analysis here, and then we can also look at the factor of safety for the winter conditions. So if we then go to the output program, so here we see the results for the safety analysis, where we actually see that the groundwater table has changed due to the high rainfall. So it's now having this shape, the slip surface information. So we can go again to the incremental deviatoric strain, and we can see that we have a very similar mechanism here. Now we again go to the chart. We can see here with the red line, which is now the winter condition state, that we have a reduced factor of safety and is even below 1.3 in this case. So that was not enough. So in order to make sure that we have a proper safe design of the road, the design was proposed to install soil nails. So if we go back to the input program, first idea was to construct only a top nail here to see if we would reach the required factor of safety. So that would be 1.8 factor of safety against loss of the road and a serviceability factor of safety of 1.6 for the top. Now if we then go to this analysis, and again we see here the slip surface mechanism. So if we go to the incremental displacements, we can see that the slip surface has changed its shape a little bit. You can see that it doesn't have this slip surface, which is a bit deeper, but the soil nail here restrict this failure surface, and so it has a enhanced stability. The question of course is how much. So again, go to the curves. So here we have the new design. You can see here with the added purple line that we do have an increase in the factor of safety, but as you can see, it's still here at factor of safety of about 1.5, and that is still not enough for the required factor of safety for this design. So the design was updated to show that 3 rows of soil nails were installed. And if we then go to the output program again for this final stage, we see again here our deformed mesh. And if we go again to the incremental displacements, we can see now that the slip circle with the lowest factor of safety in our finite element analysis using PLAXIS 2D is now switched to the top slope. And this is of course the part where we would need to have a minimum requirement of 1.6 for the factor of safety. So let's go to the curve to see if indeed this factor of safety has been achieved. So the case where we have installed 3 soil nails is here represented by the green line, and we can see that for this case the slip surface with the lowest factor of safety is here 1.81. And that's actually for, if I put them the windows side by side, so the upper slope here is the most critical in terms of the factor of safety. And by that we can conclude that the whole design is safe enough, because the lowest factor of safety that we have in the model is above 1.8, which was the minimum requirement for the total loss of the road. So with this we've shown that we can achieve the required safety. But the question is, can we have more information and have a better insight of the factor of safety for the top slope, for the upper slope, for the and for the loss of the road? A PLAXIS finite element calculation, we can only achieve one factor of safety, a global factor of safety for the entire model. And then the resulting slip surface is the outcome. And now with the limit equilibrium solution using Slope W, we will be able to specify different areas where we will determine the factor of safety for. Now with the new tool that we have developed, we will be able to start investigating this starting from PLAXIS. So you can download this tool for Bentley Communities, and here we can go to a Python tool. So we'll start the LEM converter tool. In order to do this, we have to start the remote scripting server, because it will dynamically read the information from the PLAXIS application. So we can start the server. And now the PLAXIS 2D to limit equilibrium model converter is loaded. Now we can update the data we get from PLAXIS, or we can select a specific phase that we want to select here. In this case, I want to get the winter conditions. So this is before installing the soil nails. Now this tool is able to use Slope W as the limit equilibrium solution. Now in order to easily start our calculation in Slope W, we have to select the right slip surface direction. Now in this case, it will be from left to right. And with this conversion, we will be able to convert the geometry of this construction stage together with the material assignments. And if the strength properties in PLAXIS are the same as in Geostudio, it will take them and copy them to a Geostudio file. Loads are included as well, and the same for the reinforcement elements that we have constructed in the subsequent phases here, as well as the water table, which is of course very important because it has a very important effect on the factor of safety. Now if we then hit convert, the model will be read from the application here. The window here will give you some information about what happened in the model. So the window here will give us some warnings and hints, and we can directly launch Slope W from this button here if Slope W is installed in the default location. So if we click this, you will see that Slope W will be loaded. And now it's time also to switch to the Slope W demonstration. And we're back here. So we had seen the PLAXIS model. Now we have done the conversion, and now we're going to do the limit equilibrium analysis on the winter condition. And serviceability requirements dictate that indeed the minimum factor of safety against total loss of the road would be 1.8. And see here highlighted at the top is that for this part, the top of the slope, where we actually get a temporary shutdown from the road, is at 1.6. For the total loss of the road, we're going to have a look at the lower slope failure, but also the global condition, because both the lower slope and the global condition will lead to a full loss of the road. So let's get started, and Chris Callan will guide us through the Geostudio analysis.
After running the Python script, I can now open the file directly in Geostudio. If I click at the top of the analysis tree, the top node, we see all of the information from the PLAXIS project has been passed over to Geostudio, including the unit settings. Notice we have one geometry added to the analysis and to the project, and then one slope stability analysis under this 2D geometry. I'll click on Define Project, and I'm just going to rename this analysis in the name dialog box to A, upper slope. You'll notice underneath us here in the Settings tab that the analysis type is set to Morgenstern price. And that, of course, is a rigorous method, and so we have selected a half-sine inter-column force function. The pore water pressure conditions are correctly set to come from a piezometric line. We see it defined in the background on the screen. On the slip surface tab, we have left to right for the direction of movement, and we're going to search for the critical using entry-exit. I'll turn on optimization, which uses a Monte Carlo random walk procedure to find a slip surface shape that might produce a lower factor of safety. That done, I'll close the dialog box and click on the Draw Entry-Exit. Okay, moving that over, I'm going to drag open the entry zone up near the top of the slope, and then change the exit to be a point, which I will draw at the toe right there, and just adjust that a little bit. Okay, with that done, I'll change the number of increments for searching in the entry zone to 10, and the number of radius increments also to 10. Okay, I'll close this dialog box. Notice that the piezometric surface is above the ground surface, and so a water surcharge load is automatically applied. In the Solve Manager, I'll start the solver for our one analysis. When it's done, we switch into Results View, just change the zoom, and we see that the factor of safety is 1.8 and the critical slip surface is located near the crest of the slope as expected. I'll go back to Definition View, click on Define Project, right-click Analysis A, and add a clone of the analysis. I'll then rename it to B, Lower Slope. Cloning brings everything forward, and so I do not need to change anything in the tabs. I'll clone one more time and rename this to C, Global Stability. Okay, again, clicking on the Slip Surface tab, we see that everything came forward. Close this, click on Analysis B, and now I'm going to just change the entry and exit zones for the lower slope search by first changing that to a range, drawing the exit zone down near the toe of the slope, and then I'll adjust the entry to be along the road surface. Change the number of increments to 10, and then click on Analysis C, and I'm going to do the same thing here. But I'll actually show you, if I close this, I can go to Define, Replace in Analyses. And this dialog box takes any object, in this case the slip surface definition, and it pushes it down to any other analyses in the tree. So now Analysis B and C have the exact same slip surface definition. Click on Analysis C and then go back to Draw, Entry, Exit, and I'm just going to move the entry zone up to the upper portion of the slope to do our global stability check. That done, I'll close this dialog box and point out that the surcharge load also came over from PLAXIS. I forgot to do that before. So if I click on Define Surcharge Load, we see two of them. Both of them have a surcharge unit weight of 10 kilonewtons per cubic meter, and it is drawn at 1 meter above the ground surface, giving us a stress of 10 kPa. I'll solve all three analyses. In Results View, we see that the factor of safety is 1.26. It's going to change the font size under View Preferences to 12. Close this. So again, 1.26 for the critical. And then if I click on Analysis C, we see a factor of safety of around 1.5. Okay, I'm going to click on Analysis A and draw graph. I will add a new graph and rename it Convergence. And then from the kind dropdown, I'll change the category from Slice Data to Convergence Data. Here we're looking at a plot of factor of safety versus lambda. And as I discussed in the PowerPoint, we want clean, unambiguous crossover between the moment and force factor of safety lines, which we see here for both the optimized and unoptimized slip surface for Analysis A. Okay, we'll go back to the slip surface window and just note that all of these look very good. And then Analysis B, check this one. Again, the convergence is nice and clean for both the optimized and unoptimized. Now in contrast, in Analysis C, this is not an unambiguous convergence for the optimized slip surface. We can see that those points barely cross, and regardless of the lambda, they're almost all conceivably converge. So it's quite ambiguous here. Okay, with that, I'll close this and go back to the PowerPoint slides.
So thanks to Chris for doing this quick demonstration for Slope W. So just as a quick summary, if we look at the upper slope, the factor of safety would be 1.8. If we look at the requirement, it would be 1.6, so that is satisfied. If we look at the lower slope, just focusing on the lower slope, it would be 1.26, which of course is much lower compared to the requirement that we had for 1.8. And if we look at the global stability, the overall slope, we see that we reach a value of 1.6, but also with the notice that we should always check the convergence for this lambda parameter. So the optimized slip surface that is done is questionable if that would be the true factor of safety for this one. So maybe then you should not look at the optimized one, and at least the factor of safety will be larger than 1.6. But yeah, still 1.6 is lower than 1.8. And as we also see is that the lower slope is the most critical one that we have. And if we look at the lambda parameter, we have to sort of make sure that at least we can check the convergence to making sure that we indeed have a proper converged solution. Now, to go quickly over the example that we did here today is that we see that if we look at the initial slope, this is also good for a verification. If we just compare slope W with PLAXIS 2D, do they give comparable results if we just run the initial slope? PLAXIS 2D gives a factor of safety of 1.25, while slope W gives 1.29. They still give the same slip surface, so it gives us good confidence that we indeed have something to take care, that we have a good representation from both models, and that we can really compare the factor of safety. Now, if we look at summer conditions, so where we have the horizontal water table, so the water table is still low, there's not much rainfall yet, and if we look at the slope W analysis compared to PLAXIS 2D, we look at the upper slope, which is 1.8. So this already satisfies the condition. So we don't have to do anything for the upper slope from summer and winter conditions. If we look at the lower slope, there are the two methods that we can analyze the effect of the road. So we can take the road into account that we do not expect the road to fail, that the slip surface will pass through the road. If you have like maybe a concrete plates, this kind of road construction, it's very unlikely that you will get a failure through the road. So then we can get a factor of safety 1.4. If we consider the road to be weak, think of a tarmac or a bituminous kind of road, or maybe just have a gravel road. Then the factor of safety determination might give you a slip surface that will pass through the road. So we considered both in slope W. In PLAXIS, we actually have a plate element to represent the road. So in that case, we do not get failure at the through the road. But the factor of safety for PLAXIS gives us 1.3 for this lower slope, and for slope W, it's between 1.3 and 1.4. Depending on the construction of the road. Now, if we go to the winter conditions, so that's what also what we have shown also in the demonstration from Chris, is that PLAXIS 2D gives us this factor of safety also about 1.3 for the lower slope. So you see it doesn't make much difference in terms of the road installed, but still we have a factor of safety 1.3, which is of course much too low compared to other requirements. Now we can run different analyses in slope W, the upper slope, which is at the let me show you, which is this one here, and then we can look at the slope global stability, which we seen that it's 1.6, but the convergence is something that we really have to look into if we can trust the lowest optimized value, and then the weak and strong road gives us a factor of safety between 1.3 and 1.25. So the results are very comparable. Now, if we go to a solution, we actually install one soil nail. So with PLAXIS 2D, we saw that we have an increase in the factor of safety. It's going to approach 1.6, still not sufficient. And if we look at the limit equilibrium solution, you'll see that the slope W upper slope is still 1.8, so that would be this one. The global stability that we check is actually a factor of safety of 2.1, so the global stability is satisfied. But if we look at the lower slope stability, because that's of course with limit equilibrium that we can really pinpoint which part of the slope we want to take into account. We can see that with the strong road, it's a factor of safety of 2.1, while if we do not consider the road to have a serious impact in reducing so when the road doesn't have a serious impact on the factor of safety, we can see that the factor of safety actually goes to 1.6. So both PLAXIS and slope W actually show us that the lower slope is the one with the lower capacity, and also it doesn't satisfy the condition. So then the ultimate design was made that actually we have 3 soil nails, and with that actually the factor of safety in PLAXIS indeed also shifts to the top of the model at to 1.8, and the factor of safety for the upper slope in slope W stays of course 1.8 because it's the same condition as before for the upper slope. Global stability also stays at 2.1 because it goes around the zone of the reinforcements. But we do see a change in the factor of safety for the lower slope, that if we consider a strong road, it will be well above 1.8. And if we look at the weak road, we actually see that there's no total failure of the lower slope, but it's at 1.7 for just a zone just below the road. And you can argue if there would be a total loss of the road or just a temporary serviceability issue. So this is at 1.7. So with this, it could be concluded that the design is safe enough. Of course, you have to analyze a bit, sort of, okay, what can we do about the very shallow failure zone just around the corner of the road. So if we look at the overall results for the different conditions, we can see is that loss of surface factor of safety should be larger than 1.6. Is satisfied in all conditions. So the upper slope, which is adjacent to the private land, that is all satisfied. If we look at the complete loss of road, we see is that with finite element we still are at 1.3 in all cases, unless we install the 3 soil nails. And then actually the finite element solution gives 1.8 for the upper slope, but since the one slip surface with the lowest factor of safety, we can also conclude that the lower part is also above 1.8. How big that factor of safety for the lower part is, we cannot tell from the finite element solution, but we do see that that it's higher than 1.8. And for with limit equilibrium, we can see that that part would be 2.1. So from this hillside case, this is our conclusion. I see now I'm a bit over time, but we're almost at the end. So using PLAXIS 2D, we can determine the critical factor of safety for the whole model, but that does not give us the required information in this case to judge the surface closure of the road. So it will be the upper slope and the total loss of the road, lower slope and the entire slope. Applying one soil nail, it's not giving us the minimum required factor of safety in PLAXIS, and in slope W, the minimum factor of safety is depending on the influence of the road. Adding 3 soil nails gives us the required factor of safety in both the finite element solution using PLAXIS 2D and the limit equilibrium solution using Geostudio Slope W. So being able to judge both numerical solutions gives us more insight and more confidence in the final design. So as an overview, it's easy to convert your model definition from PLAXIS 2D to Geostudio. It's just a simple Python tool with a few clicks. You already can start your limit equilibrium solution starting from a PLAXIS 2D analysis, and then you can compare the two solutions to find out what you need in order to make sure that you specify the different zones. What's the most critical one? Can you judge if you reach convergence, yes or no, using this lambda value? So with that, we are able to quickly compare the results and give you more insight. So as a summary for the whole presentation today, we gave you an overview of how finite element and limit equilibrium methods work to determine the factor of safety. The limitations of the finite element is that we get one critical slip surface only, so the ones with the lowest factor of safety. That's the outcome of the finite element calculation. And when we add the limit equilibrium solution, we can find the factor of safety for non-critical areas. Easy to find spatial variation of the factor of safety, because that's also the outcome of the limit equilibrium solution, that we can not only see the most critical one, but all the trial slip surface, so you get a good idea of the spatial variation. And we can combine limit equilibrium and finite element to validate each other, both on the slip surface shape and the factor of safety, to determine if we can indeed have the same strength reduction of the two methods. And the process is now very easy and fast with this newly available Python tool. Before we go to the questions, and I have one final question for you. Today you've seen how you can easily start a Geostudio Slope W analysis from a PLAXIS 2D analysis. And of course, we're looking to you to find out what would be our next step. So what would you need to make this interoperability even better or more suited for your workflow? Maybe you want to read a Geostudio model and directly use it in PLAXIS 2D. In the current situation, we can only get one phase from PLAXIS to Slope W. Maybe you want to run many different phases in one go. Now, of course, you have to do it phase by phase, but maybe you also want to do something more. PLAXIS can give you a groundwater flow field or a pore pressure field, and you directly want to use it in the limit equilibrium analysis to enhance it. In the case that we've shown here today, the flow field is such that we can assume that with flow velocities that we can actually have we can use the water table as a very representative method to determine the pore pressures, but maybe you also want to use the groundwater flow field or the excess pore pressure field. In Slope W, we can also do a stress-based stability analysis using the combination with sigma. Maybe it's something that you might be interested in, or maybe you have other ideas to enhance interoperability. Please give the ones that would help you the most, because that's what we're looking for, to sort of enhance this interoperability and make your geotechnical analysis life a lot easier. I think that will be the idea that we want to convey, is that we want to listen to you to find out what you need to enhance your work right now. All right, I'll go to the resources and reference, so make sure that you submit it right now. So resources and references, you can find it also in the related content, how to run a limit equilibrium method analysis from PLAXIS 2D. So that's the page that we have, including instructions and Python script. The example case tutorial that we showed here today, there's a full tutorial case described here as well, also available in Bentley communities. The paper to determine the nonlinear finite element analysis of the factor of safety, so the basis of the phi C reduction. Some background information on how factors of safety are defined in PLAXIS. So we have a whole hour defined on that. Introduction to Slope W and a Slope W basics training. They are both available also through the resources. So let's see what we get from the results here. Is that I'm happy that a lot of people voted here, so that gives us good insight what to do next. If I see is that everybody wants to have something more, you can see that people could answer it with multiple choices. So that's why you see the high percentages. But you also see is that The two favors here are that we want to have multiple phases from PLAXIS to Slope W, and stress stresses calculated in PLAXIS to run them in a stress-based stability in Slope W are the top two. So thank you for that. So now it's time to open the Q&A box to answer your questions. I still have about 10-15 minutes to answer your questions. So go to the Q&A box to put in your question. If I don't have enough time to answer all the questions, I will follow up. So I will answer you anyway. We have the resources list. So click on this paperclip icon, and then it'll show you the resources list, and then we'll be able to you'll be able to reach all those links. And we also have access to the survey. If you have any comments, recommendations, or that you would like to see something else, or want to see me improve my skills, please put them in the survey. Certificates will be added to learn.bentley.com/transcript, and make sure that your profile and your email match. All right, time to read the questions. I see some questions here. Let's see. I see here, thank you. So you're welcome. Question from Homan from Afri. Does Geostudio have an undrained soil model with anisotropic properties like NGI-ADP and PLAXIS? Yes, Geostudio has anisotropic models, but you have to specify the directions up front. With the NGI-ADP model, which is available in PLAXIS, which is have an active part, a direct shear part, and a passive part, where actually the stress history determines the anisotropic behavior of the soil. So it can make a difference if you, for instance, have your soil loaded in compression or in extension or in shear. So that's only possible if you have a model which is has the stress history taken into account. So that can be taken with NGI-ADP. But in Geostudio, you can also have these anisotropic models, but you have to specify the direction up front. Question from Amir on what's the meaning of a strong road? Even with a strong road, the soil beneath might fail locally. Yeah, I think you're right. So if we look at the model, let's go to the definition of the case. Here we are. So if we look at the case, where we actually, let's see if I can draw here. We actually here we have the road. Yeah, you have to see if the factor of safety that you determine and the slip surface, if the road has an impact on that analysis. So if you look at PLAXIS 2D, we will assume this with the plate element, and then we do not see any failure. Of course, we can also use an elastoplastic material that we actually have some kind of plasticity introduced into this road, which we didn't do for this case. We just have a full elastic plate, and with that we actually prevent that any slip surface can develop through this. Of course, the soil might fail locally, but the PLAXIS analysis doesn't give you that result. We saw that this happened with the limit equilibrium solution, where actually we had a very localized failure around this area with the limit equilibrium solution, while the PLAXIS analysis would follow the difference between the weathered siltstone and the intact siltstone, and we just have a slip surface like this. So that's of course something that you have to judge as the geotechnical engineer, is would I expect any local failure? And the question would be that, say that we have some kind of failure in this. Oh, let me take a different color to highlight this. So if we have this kind of failure here, it's represented by the yellow line. The question is, if you have a very strong and stiff road, if this might fail locally, maybe there can be some kind of redistribution of stresses such that actually we might have a start of a slip surface, but actually it cannot fully develop because the strong and stiff road actually prevents that mechanism to really occur. So that's also something to take into account to judge how that works. So maybe it fails, maybe starts to fail locally, but the full mechanism cannot really develop such that it will lead to a full slip circle. So I hope that answers your question. Let me see. Question from Anush from Sweco. When converting finite element to limit equilibrium from PLAXIS to Geostudio, it looks like you have to define the direction of the slip surface. In the calculation where you need to check failure in both directions, how to approach the calculation in limit equilibrium? Do we need to convert twice and do separate calculations? No, and that's not necessary. What you can do, and that's also shown by Chris Callan in the demonstration, is that you can clone an existing model, and then inside Geostudio you can change the slip surface direction. Maybe you also want to change the limit equilibrium method. So you can just click on the define project item, and then you can actually set the direction of the slip surface. So you can directly change that in Geostudio. What we do in PLAXIS is that we give an initial direction such that you are quickly able to run your analysis in Geostudio without going through all the different settings and different menus, because we have seen that people want to go quickly from one to the other, and then they forget to set a certain thing, and then you have to go into the setting structure. So that's also not that convenient. So that's why we made it available as a selection up front to help you with that process. A question from Kusha is he wants to know how to give the interface between two materials deposited in Geostudio. I'm not exactly sure what you mean, because normally if you would put two soil layers on top of each other, that interface is automatically taken into account by the difference of the strength properties. We also saw that when we looked at the model, that actually the limit equilibrium and the finite element solution would actually follow a bit of the transition between the intact siltstone, and that's the lower layer, and the topsoil layer, which would be the weathered siltstone. If you really want to have like a weak plane, you can define a weak plane in Geostudio to actually have maybe some kind of special interface between the materials, but otherwise it will be implicitly taken into account. A question from Khaled from WSP. What do we do when the solution in slope W is not converged? So that means that we had to look at this lambda parameter, where actually the optimized solution did not reach a converged solution. That doesn't mean that we cannot calculate this factor of safety for the slope, but what we saw is that the non-converged solution actually gave us a result. And when you're looking at an optimized solution, you will try to find, based on the circular slip surface or the half sine kind of shape of the slip circle, is that we try to find the optimized solution based on that initial analysis and try to find a lower factor of safety around that original trial slip surface. So then maybe you're not able to trust this optimized result, but you can trust the non-optimized result. So the one so that will give you probably a higher factor of safety. So then you can say that the factor of safety is at least this value. So we can still solve the problem, but you cannot not rely on the optimized one. another solution that you sort of try to find more iterations or use more. So with this entry and exit point, we specify the number of intervals that we want to generate slips, trial slip surface, that you increase the number of trial slip surfaces there. So that can also help you to pinpoint that. A question from Gian: should be any way of modifying strength externally before being used for slope W? Now, what we have in PLAXIS is that we have material models with a certain strength definition. And we assume that we can have the same strength definition in slope W if we, for instance, have the Moore column or the Hook-Brown failure criterion. So that will be the case if you look at PLAXIS for the Moore column model, the hardening soil, HS small, soft soil creep. All these models use the Moore column failure criterion. Of course, the Hook-Brown model uses the Hook-Brown criterion. These can automatically be moved to slope W using the same strength criteria. So they can then be done automatically. If you have a different model, or you want to specify something else for slope W, you can in slope W update the parameters. So also, if PLAXIS does not know what kind of equivalent it would have in slope W, it will actually hint you in the feedback during the conversion process, and also to tell what has been done. For instance, the undrained material definition using undrained A in PLAXIS, we converted using the effective effective strength properties. So C dash and phi dash to send that to slope W. If you want to run an undrained analysis, of course, you have to check if that's what you want. All right. A question from Gian: does the imported model carry pore pressures from transient steady state analysis? No, that's currently not possible. We do not carry over the pore pressure field from PLAXIS. We transfer the definition of the phreatic surfaces into slope W, so those can be then used in your analysis. If you want to run another case, make sure that you set the correct boundary conditions for a CW analysis inside Geostudio and run that. I see some questions on the soil nails. So I think it's the final question that I have time for. I'll try to follow up with other people outside this analysis. Sorry, I didn't have enough time for that today. But something to say about the soil nails. PLAXIS can convert the soil nails. There's a nice description on how this could be done in the demonstration case. Use the link to the tutorial case to get that document. If you take a realistic pull-out force for your soil nail in PLAXIS and use the same inside slope W, then you can use that. Now, in the original definition of the case that we have here, we didn't want the pull-out force to be a limiting factor for the design. So actually, we put it to an arbitrary high value. You have to realize that you have to put in a realistic pull-out force for your soil nails to have a proper definition in slope W, because slope W analysis will assume you have a fully mobilized skin friction along your soil nail when you determine the limiting equilibrium. In PLAXIS, these developments and the skin resistance will develop from the stress definition along the piles or along the soil nails. So the mechanism there to determine that is a bit different. But in Slope W, using limited equilibrium, you have to make sure that indeed you use a very realistic upper limit for the skin resistance for your soil nails. So that's something to check, especially if you do not use the realistic values for the pull out in PLAXIS 2D, because yeah, if your design of your soil nails should not be the limiting factor. Of course, you can check that by checking the skin resistance developed inside PLAXIS, both for the plastic calculation phase as for the safety analysis. You can easily judge that, but in Slope W, it will do a full mobilization of the skin resistance when determining the factor of safety. So that's something you definitely have to take into account. All right. I see a question for how to make a seismic analysis with PLAXIS 2D. We do have an example on seismic analysis with PLAXIS 2D using dynamics. So I'll see if I can send some link. And I see some questions here from Anthony, from Pitt and Sherry. I'll make sure I will follow up later on this. I see a few other remaining questions, but I'm afraid my time is finished here today. I would like to thank you everyone for attending here, also for staying so long here to also go to the Q&A session. And I hope to see you in one of our future events. And yeah, check out our Bentley communities on the pages. And if questions, make sure to reach out to our support team. So thank you for your time, and I hope to see you in one of our future events. Thank you and bye.